So I've just started the recording. So we know for a 3D manipulator, we can solve the forward kinematic problem using the DH algorithm. So So this was covered by David a couple of weeks ago. And we use this to derive the full homogeneous transformation matrix. From the base frame. To the end effector frame. So this gives us a transformation matrix that takes a point in our kind of mobile frame that sits on our end effector. So this is our end effector mount point. This is the axis attached to it. We have a fixed base frame. We might have a series of joints in between these 2 points. But the DH algorithm allows us to construct the homogeneous transformation equation that places a point within this frame, so the end effector, with respect to our fixed base coordinate system. So everything is always in reference to this fixed base coordinate system. And as our end effector moves around, our homogeneous transformation matrix will allow us to locate that point at the end effector within our fixed base frame. And we do this by multiplying together the individual frame-to-frame transformations that we come up with through the DH algorithm. Okay. So simple robot configurations. That's the basis of a SCARA robot that we've touched on now and again, and I think David covered that as an example within his lectures. So that pictorially is essentially what we're doing. We're taking a point that we can describe easily in our end effector frame and coming up with a matrix way of describing its position relative to our fixed base coordinate system. Okay? Hopefully you recall that the final HTM, the final homogeneous transformation matrix, is composed of a few parts. And they are a rotational element and a translation. Okay, so within this overall matrix, so for 3D case it's a 4x4 matrix, we have a rotational element that's made up of a 3x3 matrix, which describes a rotation around an X, Y, or a Z axis in 3 dimensions, but also we have a translational element T, which is a 3-row vector that describes the translation of the end effector from our fixed base coordinate system origin. Okay? So this we know. So within that matrix, T is the position of the end effector. With respect to the base coordinate system. And if you go through the process for a given manipulator, you'll come up with a series of matrices that you multiply together, and you end up with quite a complex or kind of a 4x4 matrix that can contain a lot of terms to describe both the rotation and the translation. And for example, this may look something like Okay, so we'll end up with a matrix where the T element is something like that, so fairly complex. Okay, and you may have spotted this or not, if we know within that vector there, if we know our link parameters, so our fixed link lengths A1, A2, A3, A4, etc., and our joint variables, we can plug those numbers in, and that will give us the x, y, z coordinates of our end effector. Okay? Okay, so that's something that we know. Okay, so what we can say is that. So we have a set of equations, forward equations, that we can solve for our manipulator configuration. So we pose the manipulator, we know A's throughout, we know theta's throughout our joint variables to obtain that pose, and we can calculate Px, Py, Pz. What we could solve at this point is we could solve instead for theta 1, theta 2, our joint variables. The A1s, the A2, A3, A4 are all fixed. But we could solve that instead for theta 1, theta 2. Okay? But that's not straightforward. It's a set of nonlinear equations, so it will give us a bit of grief to solve that, especially if you were sat in an examination and I was asking you to solve that for theta 1, theta 2 for a given px0, py0, pz0. Okay? And we would require a different approach to solve that. Okay, so that's just stepping back a bit to something I mentioned last week, two approaches to solving our inverse problem. There's a numerical approach and analytical approach. The numerical approach would involve solving that system of equations for theta 1, theta 2, given px0, py0, pz0. But I introduced last week, hopefully, from your point of view, a simpler approach, and that's one of kind of a geometrical stand-in. So you take certain views of our robot manipulator that allow you to reduce the dimensionality of the problem by one. And from that, you can use simple trigonometric relationships, Pythagoras, the rule of cosines, etc., to come up with a set of equations that you can solve to give you the inverse kinematic solution. Okay, so that's where we got to last week, and we looked at a simple couple of simple examples. So what I'm going to do now is stretch that out a bit further, look at a few other examples, and give you a few pointers towards problems that you'll encounter in terms of the coursework, and should it come up as a question on the exam. Okay? But the one thing I do need to say is this approach, this geometric observation approach, is okay for simple robotic manipulators, manipulators of moderate complexity. And moderate complexity includes all the ones we looked at early on. So we had the Cartesian robot, cylindrical robot, spherical robot, and articulated robot are the main ones that we've looked at. Also there's the class of 2D planar arms as well. They're quite simple. So all those robotic manipulators are fairly straightforward to analyze using the method that we started looking at last week. Okay, so we just refer to this approach as the approach of geometric observation. And there's a couple of steps involved here. We look at our manipulator, our 3D manipulator. We look at it from a top-down view, which removes movement in one dimension, so we don't see any movement in the vertical direction. And then we view it from the side, and then we remove any movement kind of into and out of the page, as you'll see here. So again, it removes a dimension. It gives us a problem where we can look geometrically at the situation. We can introduce a few triangular elements into our view, our geometric view of that problem, and we're able then to extract some fairly simple, fairly straightforward to solve equations. Okay. For simple robotic manipulators, very easy. These equations drop out. For something that's a bit more complex, it can take a bit more time and thought. Okay. So a view from above and from the side, each of the views removes your view of movement in one of the dimensions. we construct some triangles from those views. Typically, what we'd be looking for is a right angle triangle, and also there will be another triangle that's non-right angled. Okay, that's typically what we're looking for when we're looking to solve using this approach. So a couple of triangles that come together that allow us to solve for our joint variables for a given x, y, z. Okay. Excuse me. So the position of the end effector is the desired point, and we want to come up with a set of relationships that relate the desired position with our joint variables. Which are the unknowns in this situation, okay? And from that, we can come up with an analytical solution for theta 1, theta 2, and so on, or if we have prismatic joints d1, d2, and so on. So we can come up with expressions that we can easily solve for our joint variables for a given end effector point in space that we're trying to reach. Okay, so I started with a couple of examples last week, simple planar arm, and then I went on to look at the Cartesian robotic manipulator. I think I mentioned last week, to suffice to say, those examples are relatively easy, relatively straightforward, so neither would come up in the form of an exam question. So you won't get a Cartesian robot as a problem in an exam, or a simple planar arm. But if you remember from last week, the 2D planar arm, two-link 2D planar arm, can be found within 3D manipulators. Okay, so knowing the solution to a 2D two-link planar arm can help you solve a more complex 3D problem. So, further examples. So we've got a robotic manipulator here that's composed of a rotational joint at the base, so that's movement into and out of the board as we look at it, and we've got a prismatic joint that moves our end effector mount point across the plane of the board in that view. Okay, so if the rotational joint on the bottom, this will become important in a bit for later for this example and later examples. As that rotational joint moves, your view of that will change. Okay, our prismatic joint will move into the board and out of the board depending on what the rotation of the base joint is. Okay, so our view will change depending on what's happening with that rotational joint at the bottom. Okay, so I've got some points to make about that in a bit. So we can draw in our fixed base coordinate frame. For the inverse kinematic approach, I'm not really bothered about the rest of the sets of coordinate axes along our robot manipulator. You do need to introduce all of those when you do a forward analysis, but for this inverse analysis, you don't need to draw in all the frames, but you do really need to draw in our fixed base frame, at least. And just a reminder, should I do that now? Yeah. Won't do that, keep it 2D. The way we look at prismatic joints, as I mentioned previously, each prismatic joint will have a fixed displacement that's down to its mechanical structure. And the joint variable, which gives us an indication of the amount of extension, amount of retraction of the joint. Okay. So A is always fixed, that's fixed in the mechanical structure of the joint. D is our joint variable for a prismatic joint. So here I've just shown the fully retracted state of the joint and then an extended state of the joint. When you come to, or if you're asked to draw a problem, or if you're presented with a problem, the A's may be 0, or if there are arrays involved that you put into your drawing, you can say, for this answer, I'm going to consider the A's to be 0. Okay? And that will just simplify your solution a little bit. So we have a vertical displacement of A1, which is a fixed link that's, again, non-flexible. Remember that. We have another link at 90 degrees to that, which is A2. And then we have the final displacement to our end effector mount point, which is A3. And our joint variable is D1. And our joint variable at the bottom is θ1. Okay? And we're looking to come up with a solution that allows us to extract θ1, d1, our joint variables for a given px0, y0, z0. So take two views, one from the side, one from above, or one from above, one from the side. the order you do it in can matter. And from the side, we look along the y0 axis. From above down along the z-axis. Okay, and then we extract any appropriate equations that come out of our views. Okay, so that's just really restating what I've said previously. Okay, so if we look at that manipulator, we look at it first from the side. And we draw out what we can see. Okay, so that's our side-on view. So what can we extract from this? Okay, so we're looking for anything that gives us movement in the x or the y direction. Okay, does anybody want to say what we can get from there? Anyone? Whoops. Yep. And that's fairly simple. That's fixed to the geometry of the problem. Anything else from that view?
Are we assuming that we've rotated around the bottom, or do we have zero rotation?
You have to assume the joint variable so it can rotate.
Then we technically don't have any other information.
Yeah, indeed. So you could immediately jump to the conclusion you can get an equation for that for x0, which would be a2 plus a3 plus d1, and then rearrange for d. But what happens is your view of a2, a3, d1 changes as your base frame rotates. So if you were to simply say x0 equals, a2 plus a3 plus d1, and that's that length there from that view, so you're viewing from the side on. But as θ1 changes and it moves, your view of that length changes as well. So you can't simply say relative to our fixed x0 coordinate system that length just is a dependent on a2, a3 and d1. Because as it moves and theta was 90 degrees, you wouldn't see anything there. Does that make sense? Yeah, so your view of that top link with the prismatic joint in, as theta moves, your base joint moves, your view of that length, your view of that distance changes with θ1. So that's all we can get from there, which is an expression for pz0, but that is fixed. There's no variation vertically, so nothing can change there. So we then go to a view from above. And this comment I'm going to make now is crucial when doing this. You want to pose the robot, and it should become obvious why in a moment. I touched on it last week as well. Pose the robot so it's not in the rest position, okay? So we want to pose the robot so it's not in the rest position, so we're going to apply an amount of rotation to our joint that's on the base, our rotational joint. So we have our very badly drawn rotational joint, we have the fixed link to the prismatic joint, and out to our end effector mount point. So normally you look to draw the system so it gives you an angle that's neither 0 or 90, somewhere in between, that gives you room to play as you introduce the triangles to come up with a final solution. Okay, so you have to be careful when drawing out your robot posed not to introduce any kind of 90-degree angles. So you don't want anything aligned with either the x or the y or the z axis, for example. Not in the rest position. And from this view, we've removed any movement in z, although for this movement in z. Anyway, and we can see movement within our plane x0, y0. And then what we do is we look, as I said, once we've drawn it, we look for triangles, and we're typically looking for a right angle triangle, and we may want a non-right angle triangle as well. For this one, relatively straightforward. We have a right angle triangle here. and we apply simple trigonometric rules. So we're talking Pythagoras, cosine rule, etc. SOHCAHTOA, if you remember that from high school, to come up with expressions for our joint variable. Okay, so for this one, it's really straightforward. We've got our situation there. So we're looking, say, for our joint variable of, say, θ1 here. Okay, does anybody want to have a guess at what that may be? So from this view, we know px0, py0. That's our given start point. What was function I taught? Sorry?
Uptangent, is it?
Yeah. So remember last week when I talked about the a tan 2 function, that's y0 over x0. Okay, so we have equation 1, equation 2, where we know y0, x0, so we can get θ1 in the correct quadrant, and that was the purpose of using our a tan 2 function from last week. And then we've introduced a right angle triangle, so the other thing we know, if we've got x0 and y0, is we know that value there, that's simply the hypotenuse of that right angle triangle, and that's a function of our desired x coordinate, y coordinate. Okay? And then we just manipulate that. And that gives us our third equation that gives us our full solution in effect. So now for a given px0, py0, pz0, we can come up with the joint variables required to reach that position within our robot's work envelope. Once you come up with a solution, part of the whole control system for the robot could then use the forward kinematic equations I've just seen. You put that as a solution back in, and you check that that position you end up coming up with through the forward kinematic equations is actually allowed within your workspace. So you can use the forward kinematic solution as a bit of feedback to say, is your solution allowed, or is that within a region that's forbidden because there's an obstacle in the way, or are you trying to push the robot through the ground below its kind of fixed concrete base in a factory floor, for example. Okay? So that robot is one that we haven't really seen before as such. It's kind of a bit of a made-up manipulator. But if you think of what we've got here, if we reduce A2 to 0, for example, we end up with a rotational joint. No, I didn't want to do that. What do I want to do? We've got no variation, no variability in the vertical direction for this manipulator. So if we introduce a prismatic joint within that vertical column, we then got variability in the vertical direction. And then if we reduce A2 to 0, which would put the next prismatic joint directly on top of that, we end up with that situation. So we've got rotation, so into and out of the board. We've got variation through the prismatic joint, vertically. Call that D1 here, and then we've got variation, which from this view would be in the plane of the board. But remember, because of the rotational joint, it's not always in the plane of the board, depends on the angle set by θ1. Okay? I'm not going to solve that one. Maybe worth you having a look at that, should you wish, and see if you can work out a solution for that type of robot. What type of robot is it, did I say? Think about what the joints are doing and what kind of shape it's going to draw out for a work envelope. Yeah, so I did hear that, cylindrical. That's indeed what it is. Okay, cool. So that brings us to 10.2. So we'll have a pause there for 5 minutes, and then I'll continue with a few more examples, and we'll bring this subject of inverse kinematics to a close. Okay. So, as I've said already, we're working with a limited number of robots within the class of industrial robot. So if the best advice I can give you to prep for the exam is try the DH approach and the inverse approach and all of those robots, and make sure you're comfortable with kind of the actual technical approach of coming up with the solutions for both. Okay, so I've just got a couple more examples to show. So that first example that we've just gone through was relatively straightforward. You can make it slightly more complex by introducing another joint. And we can go a bit more complex by introducing more revolute joints. Okay, so I made that statement I think in the first week. The more revolute joints, the more complex the robotic manipulator is to analyze. So we're going to look at a robot called SCARA. SCARA stands for Semi-Compliant Articulated Robot Arm. What it means, just to touch on, this is not examinable, is semi-compliant means it's flexible in a limited number of directions, and inflexible or fairly rigid in another direction. Okay, and this will make more sense when I draw it out. But that's just really to explain what is meant by SCARA. So semi-compliant articulated robot arm. So we have our fixed base, so that's within whatever setting the robot is in. At the base we have a revolute joint, a fixed vertical link and a fixed horizontal link to a second revolute joint, and again we have the same configuration out to the end effector mount point. Okay, so from that limited picture of a SCARA robot, we have a robot that's capable of moving the end effector flexibly within the XY plane. But it's rigid in the Z direction, so it doesn't change in the Z direction, but we are compliant across the X0, Y0 plane. Okay? I said it's a limited view of the SCARA robot. For a full SCARA robot, and I'm not going to go to that extent here, at the end effector we may have a further prismatic joint that gives us some ability to move a tool tip into and out of our work envelope. So typically a SCARA robot may have a pick and place operation, so it'd have a claw, it'd have a prismatic joint and a claw at the bottom of the prismatic joint at the end. So this is just an extension of the previous diagram. Okay, so this would be attached here on the end of that robot. That gives it an ability to reach into the work envelope and out of the work envelope pick something up. It may be a screw driving attachment that would be rotational, that can drive a screw using a combination of a revolute joint and a prismatic joint down into a workpiece, and they're commonly used for assembly as well for that purpose. Okay, but for this example, we don't have any variability in Z. So no variable in Z0. So a point in space with respect to our Z0 axis is given by combination of the fixed link lengths. Okay. So as the previous example, that's quite straightforward. So that's all we can gain really from that view, for the same reasons as the previous one, as θ1 and θ2 vary. That changes kind of the length you can see in the plane of the board. So as it moves into the board, out of the board, that changes what you can actually see. So you just see the projection of links A2 and A4 onto the plane of the board from its position. So as I said, as you move θ1 and the link arm moves into the board, you see a projection onto that plane in front of you, which is shorter. I hope that does make sense to everyone, yeah? Yeah, okay. And obviously if it rotates 90 degrees into the board, you don't see any of it, so those link lengths then disappear into that dimension that you've removed from that view. So that one's quite straightforward. Then what we're going to do is view the arm from above. Not at rest. Okay, so that's key to these problems, is to draw the configuration of the arm not at rest, to allow you to introduce these triangular elements into the drawing that will allow you to solve the problem. So if we look from above, we see down from above the revolute joint, whose variable is θ1. We have a link to a second revolute joint, and then another link to the position we mount our end effector. So that's looking down from above. And what we want to do there is look at what triangles we can introduce. I said earlier on, typically that would be right angle triangles or non-right angle triangle, and those triangles would typically share the or one side of the non-right angle triangle would share the hypotenuse of the right angle triangle. Okay, so what do we know from here? We always know the coordinates that we're aiming for. That's the purpose of the inverse kinematics. And we look and say, right, okay, from there we can draw a right angle triangle. So that's in green. Whoops. Okay, and we just label up the hypotenuse of that. And then what we look for is another triangle that's typically not a right angle triangle. And I will draw that one in, and that shares the hypotenuse. And for here, it's internal. There, okay? And then what we do is we start to label up what we can see from that configuration. So we know that is theta 1. We know that is theta 2. And then we look for what other angles that we can label up. So we can do, input the internal angle there, alpha 1. The angle from the horizontal axis up to that hypotenuse we call alpha 2. And then we've got a third angle we could label up alpha 3 there, okay? What else do we know? We know that is a 2 and that is a 4, okay? So they're just a linked lens taken from the previous view. So we've got two triangles, we've got a lot of angles there, so I believe we've got enough information to solve the problem. So then we start to think about the simple trigonometric relationships, and as I said, we normally rely on Pythagoras cosine rule, the SOHCAHTOA rules as well. It's simple as that, so it's trying to work out using those combination of equations to give us our joint variables, which in this case are theta 1 and theta 2. So we can start writing out what we know, which is first kind of straightforward. H2, so that's the hypotenuse, is simply from Pythagoras that, okay? So we'll label that as our first equation. And then we start to look at what else do we know from this view. So I've labelled up some angles. Can we come up with expressions for those angles? And remember, we're looking for theta 1 and theta 2, okay? Which we don't know in advance. We haven't got enough information at this point to go directly to expressions for those. What we can write down is theta 1 equals alpha 1, no it doesn't, alpha 2 minus alpha 1, okay? So we've labelled two angles there, and if we subtract alpha 1 from alpha 2, we have theta 1, okay? So we can't come up with theta 1 directly from that configuration, but can we come up with something for alpha 1 and alpha 2? If we look at alpha 2, that's the angle from the horizontal to the hypotenuse. We know both the sides, the horizontal and vertical sides, because there are px and py 0, okay? So we can write alpha 2 equals py0 over px0, okay? And we will call that our equation 2. And now what we want is an expression for alpha 1 to allow us to do anything to come up with theta 1. And I kind of touched on this last week. So we want alpha 1, which is an internal angle on that non-right angle triangle, but we know all the lengths of the sides, and we're looking for an angle within it, so we can use the cosine rule there to come up with an expression for alpha 1. And if you've forgotten what you do with the law of cosines, just revisit that. The formula, you don't have to remember. If you don't know it off the top of your head, it will be on the formula sheet that will be attached to the exam, okay? So that's what you'd end up with directly applying the cosine rule, and you rearrange that. So that's the inverse cosine of that lot, I believe. Okay. And that gives us a third equation. Okay. So in that equation number 3, we know h, that's given from our desired end effector position coordinates. We know A4 and A2, they're our fixed link lengths, so we can use that to get an angle for alpha 1. Okay, so then we have expressions for alpha 1, alpha 2, where we know everything to give alpha 1 and alpha 2, so we can then come up with a solution for theta 1. Okay, so if you were writing this up in code, program an algorithm, the order I've written there, the order you would solve them in. Okay, so you do equation 1, equation 2, equation 3, then you can solve equation 4 to come up with your revolute joint variable. Then we need an expression for theta 2. So if we look at that, we can say theta 2 equals, and if we go back to our diagram, theta 2 there, where's my laser pointer? Is 180, so theta 2, I'll just write this in, minus alpha 3. Okay, so everybody see that? So alpha 3 is the angle between A2 and A4 that I've labelled up there. And theta 2 is the angle between the extension of A2. So remember from previous work, when you draw your diagram, the amount of rotation from the home point is taken in reference or the extension of the previous link. So you extend the previous link out horizontally, out along its length, and the angle theta 2 is the angle between that extension and A4. Okay, so that's all along one line. So alpha 3 plus theta 2 is 180 degrees. So we can say that theta 2 is 180 degrees minus alpha 3. Okay. Then what we can do, so we need an expression for alpha 3. So alpha 3 is an internal angle within the non-right angle triangle. So we can again use the law of cosines to come up with an expression for alpha 3. That will give us h. And again, we're just rearranging that to give us an expression for alpha 3. That gives us an equation 5. And then that allows us to solve that, which gives us equation 6. Okay. So I think fairly straightforward. If you think back to the two-link 2D planar arm, we followed a very similar process to come up with that solution. Okay. You can choose in your solution to pose that robot arm, and I mentioned this last week, you can be elbow up or elbow down. It will come up with probably slightly different solution, not massively, but what would happen if you posed with the elbow up, for example? Your right angle triangle would kind of lie within the configuration of the arm, and your non-right angle triangle would be there. They both still share that common line on the triangles, which is the hypotenuse of the right angle triangle. So you can just solve it in a very similar way. You just come up with a slightly different set of equations, very slightly different set of equations. Okay, so finally what I want to touch on, and this is kind of linked to the coursework, so I'm not going to do the whole solution, so I just want to touch on things that you may need to think about. Whoops. So the Dobot, it's very similar to the configuration I'm going to draw out now. You have a rotational joint on the base. You have a small displacement. You have a rotational joint kind of at what we call the shoulder. So you have two joints at the shoulder, and you have a fixed link, and you have a rotational joint at the elbow that's to another link of where the end effector is attached. And for you, there'll be a small displacement, and this is a claw at the end. Okay, so you need to take that into account when you're working out where to place your Dobot to interact with the objects that you're told. So you know how to work out, or you will know how to work out how to position the Dobot at px0, y0, z0. And as I mentioned last week, this type of robot is called, well, referred to as a palletizer robot, for example. And this here maintains Okay, so just remember that as you move the arm around, there's a set of linkages in when you look. If you look at the Dobot, that means the end effector will always remain parallel to the ground. And as I mentioned last week, that's kind of what you want if you're moving pallets around. You don't want to tip a pallet at an angle. You want to keep it flat to the ground. And the way that this is configured will naturally do that. Okay. The robot configuration is not exactly like I've drawn here. The second revolute joint is actually attached to the base, and it actuates a link rod that goes up to the elbow to rotate the elbow. But you can think of it as the joint being at the elbow in terms of the analysis. The reason for that is it places all the weight at the base of the robot, so it's quite stable. If you put a large stepper motor at the elbow, it wouldn't be as stable, and there's a lot of weight you've got to move. And it just so happens you can move everything to the bottom and use a set of linkages to drive the elbow. And again, if you haven't looked at the Dobot yet, this will all make sense when you do. Okay. So you can, in your analysis, you can pose it such as this, and here we have elbow up. Well, you could, in the analysis, do elbow down. There is a problem with that, though, as in the Dobot won't fall into that position with elbow down. It will always work elbow up. Okay, so think about it, what you want to do. You can do both to give you the correct solution, but the Dobot only works with elbow up. One other thing is, if you're searching around the internet, there's lots of examples of the geometrical approach to solving the inverse kinematics for this. There's also lots of examples about how to do it numerically, for example, solving those system of nonlinear equations. Don't go down that route, because that's not what we've covered in class, and so I also don't want to see that in an exam solution if you memorize an inverse kinematic solution using the other way, the more difficult way. That's not what the exam will be wanting. So any inverse kinematic solution in the exam will be asking for the geometric approach. Okay. So if we think about the robot, what we're looking at, and I'm not going to do the full solution here for obvious reasons. We have the base revolute joint. We'll have a cylindrical joint that sits on top of that, that's connected to another revolute joint, revolute joint on the base, a revolute joint that sits on top of that, and then another revolute joint, and then that out to our end effector mount point. What I didn't say is you can treat that end effector as simple offsets to your calculated P, X0, Y0, Z0. Okay, because it always stays in the same position, you don't have to worry about it in your solution per se. Where was I going with that? So from the top view, we are looking down along Z, so we see movement in the XY plane. We know Px0, Py0, they're given to us. So from that view, we can only get a restricted number of things, okay? And just remember what I was saying, that when our robot is moving, we have theta 1 that's moving into and out of the page. But from a top-down view, from the top-down view here, A2 and A3 are not the physical lengths that we see, they're projection of the physical lengths onto that plane. So just remember that's not what we're seeing there, okay? So you look at what equations you can get from that configuration. I'll leave you to mull over that. So from the side view, we have the base revolute joint, fixed displacement, revolute joint, and again, what we're looking to do here is draw some more triangles. So we want to start off, we look for, is there a right angle triangle I can draw here that I can make use of. So we look at that, maybe there's one here, okay, that we can make use of. Is there another triangle? There's one here that we can maybe make use of. And then what do we know? We know that angle there from the horizontal green line, the horizontal base of that right angle triangle is theta 1. That there is theta 2. If it has moved that way, remember it's negative, because that's, remember the right hand rule for rotation. Okay?
Given what we've defined above, would those be theta 2 and 3?
Who went, sorry?
Given what we've defined above, wouldn't those be theta 2 and 3?
You're quite correct. Yeah, cool. Okay, so we know those angles, but can we get anything directly from there? It may be that we need to draw in or think of some other angles, and then if we look at, say, the right angle triangle, what do we know? We could label that alpha, I don't know, whatever we want to call it, alpha 1, alpha 2. And then we have the purple triangle. What do we know within that? What can we label? There's an angle there, for example. Do we know that angle? Just think of the example we've just gone through. We know this, which means that is that. Okay, and then we go through the same process we've gone through previously. We're just working out what information we can gain from that to give us theta 1, theta 2 and theta 3 from that view. So if we can work out what alpha 1, alpha 2 and alpha 3 are, for example, we should be able to come up with expressions for theta 2 and theta 3 as we did the previous example. So I'm just wondering how much to give away. So for example, theta 2 equals, from those two triangles I've drawn alpha 3 plus alpha 1. For example, alpha 2 or alpha 3, you can come up with an expression because you would know what I'm drawing in here is A1, A2, A3. You know those distances as well. So the say the vertical dimension is our given point in space. So we will know that our PZ0, for example, is a combination of that side of the triangle plus A1. Make sense? Yeah? Okay, so I'm not going to do the whole solution because that's really the coursework, but it is really just using what we've done at the moment, but taking into account things physical with the Dobot. So the revolute joint at the base will be raised off the ground because of the kind of the building, the base block of the Dobot itself. You have to take into account the link lengths of the arms, etc. So that will give you dimensions for A1, A2, A3 to include in your solution. And then it's a case of working out how the robot is posed at rest and where its end effector is in space at that point before you start moving it. Okay, so it won't be just a simple case to reach a point x0, y0, z0. You set some angles up because the natural rest position of the robot won't just be horizontal. Okay, it will be in an opposed configuration. So you just have to work out what extra rotations you need to apply to the joints. Within the Dobot Studio, which is how you control the Dobot, you can obtain the rest angles directly from that interface. So the Dobot will be posed and you can have a look within that interface and it will tell you what the angles of the joints are. And then just play around with it in the programming environment to get a feel for how the robot moves, just simply setting the angles or asking it to adopt a position or position its end effector at x0, y0, z0, for example, and seeing what it does. Just remember, one thing for the coursework, we want you to solve the inverse kinematics for the Dobot, so you can't use the functions that do that for you, where you say simply position the arm at x, y, z, okay? You want to calculate the angles to do that for you, okay? So you'll end up with a set of equations such as this that you will have to solve within the Dobot programming environment in order to give you the joint variables that you need to position the robot at certain points in space. Or you can do the solution in MATLAB and come up with a table of angles that you can put into the Dobot. So you can simply say within the Dobot algorithm, set joint 1 to 50 degrees, joint 2 to 30 degrees, joint 3 to 20 degrees. And you've calculated those angles within MATLAB, for example. Or you can do all the work within the Dobot Studio. It has the functionality to solve the maths for you. Okay? It's up to you how you do it. Majority of people probably tend to rely on MATLAB and come up with a table of values for the angles and then simply plug that sequence in. Okay. What else did I want to do today? Okay, any questions on that? Nope. Okay. I'm going to go through, because I don't know if David did do this. I'm going to go through a certain style of question that you will see in the past papers, and it could come up on the exam. So the style of question is, okay, so let F be a fixed robot frame. So that's typically our base frame. Where's my bits? So that should be right from your point of view, if you can see that or not. So that's our fixed base frame, and that's defined as F1, F2, F3. Think of F1, F2, F3 as simply X, Y, Z. Okay, and then we have another frame, M, a mobile frame, and initially those frames will be coincident, so the origins are the same. And what will happen then is the question will describe a set of operations. Typically we would translate the mobile frame, so this moves, the fixed base frame doesn't, so we might say we move the mobile frame 2 units along this axis, which would be X, so we state the direction of movement. We might then say we move the mobile frame 1 unit along Y. So that's 2 kind of linear translations, and then we might say we then rotate the mobile frame through an angle. And the way we describe those angles is using a set of statements called, or definitions called York pitch and roll. Okay? So that set of movements, the first 2 translations, were with respect to the fixed base frame. Okay? And the rotations could be with respect to the fixed base frame, or they could be with respect to the mobile frame itself. So make sure read the question carefully to work out what you're actually rotating around. Okay? Question could ask you for a series of sketches to show each of those points or those operations. So initially coincident, then you move along one axis, move along another axis, and then rotate. So you might have to draw that out. Movements with respect to X, with F, sorry, or no, that would just be with respect to the fixed frame. you could have movements with respect to the mobile frame, and they're typically about rotational movements that are defined as yaw, pitch and roll. Okay? So typically what you would have in a robot system is you'd have the first 3 joints that will allow you to position the mobile frame, which is the frame of your end effector, in space at x, y, z, and then you would move your mobile frame, your end effector, through a set of rotations around each axis called yaw, pitch and roll to orientate your end effector with your work envelope. So notice I move along the fixed axis, because that's your reference, and then orientate your end effector by rotating it through a number of angles that are called yaw, pitch and roll. So this, you do have to remember what yaw, pitch and roll means. They define rotations around specific axes. So the formula sheet in the exam will give you the rotation matrices for rotation around x, rotation around y, rotation around z. Okay? It won't tell you which is yaw, pitch and roll. You have to remember that, but this is defined on this diagram. So think of it as an aircraft. The nose is x, isn't it? Yeah, along x. Vertical axis through the fuselage is z, and then along the wings is y. And so a yaw is kind of rotation around z. Okay. Pitch is rotation around y, so that's nose up and down. So that's the axis going along the wings. And then you've got the roll, left and right, which is along the axis through the nose, which is x. Okay, so you will have to remember which of those are which. I can't remember now if there are arrows on the x, y, z.
Yes.
That tell you the positive direction of rotation as well. So a typical question could be, this moves along x0 by something, moves along z0 by something, and then undergoes a roll, which is which is what? So which axes? Which one? That one? That one? Or that one? That one? Okay. Okay, so that would be around the x. So that's through the nose of the aircraft, for example. Okay, so that's just because if you look at the past papers, you will see these references to yaw, pitch and roll, and that's what it's talking about. It's talking about a specific direction of rotation around the specific axes. And when we're thinking about a 6 degree of freedom robot, where we have 3 major axes, 6 minor axes, 3 minor axes, the 3 minor axes are all rotation ones. One of those would be the yaw, one of those would be the roll, and one of those would be the pitch, for example. Okay? And what you'd end up doing is, the question may say, where does a unit vector or a 0.1 unit long x end up in space? Okay, so for that translation along there, you can construct a transformation matrix. Oops. So for 3D problem, the matrix will be of that form, where we have a rotation and a translation. So the question could ask you to construct a matrix for each of those operations, combine them together to come up with a full transformation matrix that you may then apply to a point that started 1 unit along that axis. Okay? So you know the coordinate of the 1 unit along that axis within its x, y, z. So it's just 1, 0, 0. You come up with a matrix to describe that movement, and then the rotation. Combine them together, apply it to that point within this coordinate frame, yeah, and that should give you the final resting place at that point after those operations with respect to our fixed base coordinate frame. So, if you're just talking about a linear translation of, say, 1 unit in Z, what is t? So that would be, for a 3D problem, a 3-row vector. What would that 3-row vector be if you want to translate 1 unit along the fixed base coordinate system? Anybody? Sorry?
Zeros. The rest are all zeros.
Oh, ignore that bottom one, that's the homogeneous bit.
Yeah, 0 to 1.
0, 0, 1, yeah? Okay. And what would the rotation be for that?
Diagonal matrix of ones, or identity matrix.
Yeah. Okay, so there's no rotation, so it's just the identity matrix, and that would be your first. So you move in 1 unit along Z, and it's a combination of those two elements to give you the full homogeneous transformation equation matrix. You do that for every described movement. So if you end up putting the end effector or the mobile base terrain through a rotation at your pitch or a roll, that R would then correspond to the rotation required around the specific axes. Okay, so you'd end up with one matrix for the movement along this axis, one matrix for the movement along another axis, and then another matrix for the amount of rotation around the specific axes corresponding to your pitch or a roll. Combine all those together, apply them to, if the problem's asking you for a 0.1 unit along the x-axis, that would be 1, 0, 0. Apply that, and then that should give you the final resting point of that unit vector along the x-axis after going through those translations. That makes sense. Makes sense if you do the examples within past papers. If you get any problem with the past papers, just let me know, and I can clear that up, because some people will try the past paper, not read the question properly, for example. So when you're doing the past papers, make sure you read the question properly, because it may specify what axes you're rotating around or moving along. Okay. And I think that brings us to a close. So you've got no more of me until the revision lesson. So you've got David for the next 2 weeks to bring you up to Easter. Then we return for, I can't remember if you have one more lesson with David or revision then. I've lost track. But we'll bring some examples. We'll just discuss a bit more about the things we talked about in the last revision session. Okay?